If you implement the standard OAuth 2.0 authorization code flow in a modern mobile, desktop, or single-page application, your login sequence contains a critical vulnerability. To understand why, we have to divide applications into two categories: confidential clients and public clients. Confidential clients run on a secure backend server, while public clients execute entirely on the user's local device, like a phone or a browser. This diagram shows their security difference. The backend vault on the left safely stores a client secret, a private password for the identity provider. The mobile app on the right cannot. Hard-coded secrets are easily extracted by decompiling the app. Without a secret, the token endpoint cannot verify the application's true identity, assuming any request is legitimate. Relying on static secrets in an environment where source code is visible guarantees eventual compromise. Securing the authorization code on public devices requires abandoning static passwords altogether. This network diagram shows the baseline OAuth login process. A legitimate mobile application initiates a request, sending the user to the authorization server. After approval, the server issues an authorization code. It redirects back using a custom URI scheme, like myapp:. But a malicious application on the same device can register that identical scheme. The operating system mistakenly routes the code directly to the attacker. The attacker sends that stolen code to the token endpoint. Since public clients lack a client secret, the endpoint accepts it without verification, issuing an access token. The attacker now controls the user's data. The standard authorization flow relies on secure network transit, but it breaks entirely when the code is intercepted locally on the user's machine. The protocol lacks a mechanism to mathematically bind the authorization code to the specific application instance that originally requested it. To solve this, the OAuth working group created an extension called Proof Key for Code Exchange, or PKCE. It replaces the vulnerable static secret with a dynamic, per-request cryptographic handshake. This diagram shows the first step of that handshake. Before the login process even begins, the client application generates a high-entropy, cryptographically random alphanumeric string called the code verifier. This verifier acts as a highly secure, one-time use password. It is stored securely in the app's local memory and never leaves the legitimate application during the initial login request. Next, the app creates a second component, known as the code challenge, which is mathematically derived directly from the verifier. The client takes the code verifier and passes it through a SHA-256 algorithm. The resulting hashed output is the code challenge. The SHA-256 algorithm functions as a one-way cryptographic hash. While the code challenge is transmitted over the public internet, it is computationally infeasible for an eavesdropper to reverse engineer that hash to recover the original code verifier. By generating a unique ephemeral secret for every individual session, PKCE tags each login attempt with its own verification state, moving away from a single secret shared across all users. Let's trace how these cryptographic components move across the network. Step 1. The client initiates the login request to the authorization server, explicitly attaching the hashed code challenge to the URL payload. The authorization server receives the request and temporarily stores this challenge in its database, keeping it associated with the login session. Step 2. The user approves the login. The server issues the authorization code and redirects it back to the client device, exactly as it did in the vulnerable flow. Step 3. The client receives the code and makes a backend request to the token endpoint to execute the final exchange. Here is the crucial addition. In this request, the client must send both the newly acquired authorization code and the original, unhashed code verifier that it kept hidden at the start. The token endpoint receives the code verifier and independently hashes it using the exact same SHA-256 algorithm. The server then compares its freshly computed hash against the original code challenge it saved in Step 1. If the hashes match perfectly, the server possesses mathematical proof that the client exchanging the token is the exact same entity that initiated the login process. The verification succeeds, and the server safely issues the access token back to the legitimate application. PKCE shifts the security model from who holds a static secret to who holds the mathematical proof of the original request. Looking at this side-by-side comparison matrix, you can see how PKCE neutralizes the original interception attack. On the right, the malicious app successfully steals the authorization code via the custom URI redirect, just as before. The attacker takes that stolen code to the token endpoint, but now the server demands the original code verifier to complete the exchange. The attacker never had the original verifier. The server attempts to compare the hashes, the check fails, and the token exchange is permanently denied. This checklist highlights 3 common errors developers make when implementing PKCE. The most critical is using the plain transformation method instead of S256. The plain method sends the verifier without hashing it. This exposes the verifier over the network, providing no cryptographic defense. Another error is assuming that HTTPS renders PKCE unnecessary. TLS and HTTPS focus on encrypting data as it travels between 2 points. They do not prevent application layer interception once the data is delivered to the operating system and becomes accessible to other apps on the user's device. An intercepted authorization code without its corresponding verifier is a useless locked ticket. PKCE entirely neutralizes the injection attack vector. Because RFC 7636 was originally drafted with mobile apps in mind, there is a widespread misconception that PKCE is only a mobile extension. Single-page applications running in modern web browsers face the exact same architectural inability to store client secrets as iOS and Android applications. Their entire source code is delivered directly to the user. Major identity providers, including Auth 2.0, Okta, and Google, now make PKCE mandatory for all public clients. They have actively deprecated older, vulnerable methods like the implicit flow in favor of the authorization code flow layered with PKCE. The industry standard now states that even confidential clients with secure backends should implement PKCE on top of their client secret. This provides defense in depth against advanced code injection attacks. User security cannot rely on static passwords that inevitably leak. True authorization demands cryptographic proof at the exact moment of exchange. What began as a mobile security patch has evolved into the non-negotiable cornerstone of all modern OAuth 2.0 infrastructure.